We're going to look at some factoring today. We've factored polynomials. We're also going to be factoring differences of cubes and sums of cubes. That'll be something that's fairly new to you probably. So we know how to factor this one, example 1, pretty basic. This is a trinomial factor, right? A is 1. So we did this last class. And of course, what you want to do is you want to find two integers that multiply to negative 18. That's the constant. And also those two integers that also add up to negative 3. And so in this case, you would have negative 6 and positive 3 would be the two numbers in question. And so what you would do with those two numbers is you would split up this trinomial into two binomials. X squared here, you'd put an x at for the first term of each binomial. And then you'd simply place those two integers in each binomial. So you'd turn this into an x minus 6 from here, and times x plus 3. So a trinomial can be factored as two binomials, especially when we have a equals 1. So that's this value right here is 1. Then it's pretty easy. Okay. Difference of squares we also talked about last day. That should be pretty straightforward. Difference of cubes, I want to show you though that a difference of cubes also has a pattern, and it's kind of similar to the difference of squares. Both have a factor of a minus b. Now a, when we're talking about difference of cubes, a is the cubed root of this number. Okay, so if it's a difference of cubes, for example, if you have x cubed, the cubed root of x cubed is just x. All right. The cubed root of 27 is what? So what cubed is 27? It's 3. Yeah. So the cubed root of 27 is 3. All right. So that's the difference of cubes. Notice this. If it's minus difference of cubes, then this is always minus. That's the same. If you have a sum of cubes, this first factor, this binomial, is also always a plus. Okay, so same sign is what we're looking for the first factor. And then this one here is, it's basically like, well, it's not similar to difference of squares here. It's a trinomial, it's like a quadratic. But you're going to have a squared is the term in both the sum and difference of cubes. You're going to have ab, so that's the multiplication of the cube roots for the middle term. And you're always going to have b squared as the last term. Okay. The only thing that's different is the signs. And again, this sign and this sign are always opposite. So if this is a minus for a difference of cubes, then this sign has to be positive. If this is a positive, and this is a positive, this has to be a minus, or a negative, or a plus. No, not a plus. And then this is always positive back here. So write this down, try and commit it to memory. You'll have this to refer to most of the time when you do it, but there are some patterns that you can take a look at there. Okay, so how do we practically use this? Well, what you're going to want to do is you're going to want to make sure that you know what some of your cubes are, and it would be good for you to memorize some of the cubes, possibly up to 10, but for the most part, I mean 5, 6, those are the ones you're going to use the most, from 2 to 6. So have those memorized would be good for you. And let's take a look at example 2a together then. So this is a sum of cubes, and the pattern is going to be this one right here. We already figured out what a was, so this factored, I'm just going to write out the whole thing here. This factored equals, okay, this is going to be a plus b, the same sign here, right? Over here, this is going to be a squared minus ab, and this is going to be a plus over here. You don't have to do it exactly like this, but I'm just trying to help you learn how these signs work. So we need to find out what a is. That's the cube root of the first term, which is x. So that's an x, and this is going to be the cube root of 27, which is 3. So that's the first factor in this sum of cubes. Good so far? The rest is easy. Take this number right here, or value, and square it. That's going to be x squared. Take this value, the second term there in the binomial, and you square it and you put it there. That's going to be 9. And finally, just do 3 times x, and that's the value that goes here. Questions?
Will there be like difference of not perfect cubes? Because like we went over the square.
Yeah, difference of not perfect cubes. Yeah, you can treat numbers as cubes. I mean, you'd have cubed roots values in here, right? So typically we don't do that. I mean, it's possible that you'll find out in calculus you would do that if you had an identical factor that you could simplify that out. So for example, if this was, it's tough for me to give you an example, but if this was 28, let's say, okay, and this was the cube root of 28, okay, that's strange, okay, and so on. This is going to, so cube root of 28 squared. What's that? That's 28 root 28. Okay? But why would we do this unless we were asked to simplify something like this? Okay, if you were asked to simplify that, then it would be good to factor this as a sum of cubes, because you see how we have a common factor now, right? And then you would be able to simplify that by dividing out a factor. So in calculus, you might have to do that. If you have some kind of strange simplification you have to do, then you might recognize this and say, hey, if I factor this as a sum of cubes, I'm actually going to get this as a factor, and boom, we'll be able to simplify. So that's a great question. I wouldn't worry about that now, but that will be something maybe in the course of this, I would say most likely that you will have to, that you will come across. Okay, any other questions? Sometimes hypotheticals are a little difficult. Like, what if this and this and that? Well, yeah, sometimes I can answer those, sometimes I can't, but it's a good question. Okay, this one over here, B, okay? B, what you're gonna wanna do first is make sure that you take out any greatest common factor first. That's always a question you ask yourself. Here there was no greatest common factor, so we didn't have to worry about it there. But here, certainly there's a 2 is a common factor, and an x squared is a common factor. So 2x squared is something I can take out of both of these, right? And what does that give us? That gives me x squared, I guess, minus what? 9. Okay? Okay. So this is not a difference of cubes. This actually boils down to a factor of 2x squared and a difference of squares. So that's an easy one. So we're going to go 2x squared here. This we know from years ago. X there, the square root of 9, because that's the 3, and plus, minus, and we're done. Question?
The difference of squares has to be minus 1.
Yeah, a difference of squares has to be minus. A sum of squares cannot be factored. So you can't factor that one. Yeah, I mean, you can, but the roots are not real.
Okay.
Yeah, you have complex roots. So that's not, yeah, we're not going to deal with those too much. But you would just stop here. You couldn't factor this one. Yeah. Okay. Okay, any questions? You guys good with that? All right. All right. So go ahead and do this one on your own. Just take a minute and do this one on your own. Factor this difference of cubes, x cubed minus 8. Let me know what that turns out to be. All right, so let me know if that's what you got here. Again, just following the format, take the cube root of x cubed and 8 and plug those values in there and there. This is a minus, so this has to be a minus. This is opposite, it's a plus, this is always a plus, so on. Okay? Now to check, if you do a FOIL method, well, not exactly FOIL method, we're doing distribution. FOIL method is just for binomial times binomial technically, but x times x squared is x cubed and so on. You keep multiplying down the row, and then you move to the next one, multiply through, add up all your terms, combine all your like terms, and you should end up with x cubed minus 8, which means that this is indeed the proper factored form. Now, can you factor this trinomial any further? That's a good question, right? Are there any numbers that multiply to 4, positive 4, and add to positive 2? No. So that's why we stop there. That's why that's kind of base form there. Okay? All right. Sum of cubes. Okay, again, we should try and look and see if there's a GCF here. So I would jot down this as an example here. 27a to the power of 9 plus 8b cubed. Check if there's any greatest common factors. Anything we should pull out of that first? No, it doesn't look like it. 27 factors are 3 and 9. 8 doesn't have a 3, doesn't have a 9. Two different variables, so we're good. Okay, so let's take the cubed root of this value. What is the cubed root of 27a to the 9? What's that? Cubed root? 27 is 3. The cubed root of a to the 9. So a to the power of what times itself 3 times gives us a to the 9. That's a. Is it squared or is it cubed or is it? Yeah, it's cubed. So remember what we would do to cube it is we would we would multiply this exponent by 3. So we want to divide the exponent by 3 to get the cube root. Okay. This is a plus. So is this a plus or a minus here in this first one? Plus, it's the same. Good. Cube root of 8 is 2. Good. Cube root of b cubed is b. Right on. So there's our first factor. Awesome. The next one, let's square 3a cubed. So that's going to be 9a to the what? That's right. When you square, so a cubed squared, you multiply those two. Right? It's good. Yeah. So 9a to the 6. This is a plus, so this should be a minus. You multiply these two terms, you get 6a cubed b. I like it. And then plus the square of this last term is 4b squared. All right. Any questions about that? Sums, difference of cubes. Good? All right. Calculus is easy, right? Amen. All right.
Monkeys with the symbols.
You what? Monkeys with the symbol?
Should we get one of those?
Can we get a monkey with symbols?
Yeah, and then wind it up every time we get the answer correct. We're gonna run tests, everything.
I'm kind of having deja vu right now. Have you guys been in my class before? The whole clanging symbol monkey thing? No, it hasn't happened before. Maybe I just think of that when I look at you guys. Could be that maybe. Okay. Moving on. Okay, factor theorem. Factor theorem. So again, pre-calculus 30. Factor theorem. If we have a polynomial, the factor theorem says that we do have a binomial factor of x minus some value b, if and only if, okay, if when you plug this b value into the polynomial, the result is 0. That's the factor theorem. So you do not have to do the synthetic division, which we're going to go over briefly here soon. You don't have to do all of the factoring to find the factors. You can test to see whether something is going to be a factor or not. For example, if I wanted to test, factor this, if I wanted to test to see if x, let's see, x plus 1 is a factor. Now, you should, let's back up a little bit. Possible factors, binomial factors, have to have this constant right here, must be, if you remember correctly, must be a factor of this constant term. So you would not try x plus 2, let's say, because 2 is not a factor of 3. So there's only a limited number of ones that you're going to check here. Let's do plus 1, x plus 3, x minus 1, x minus 3. Those are the ones you're going to want to check. One of those 4 could possibly be a factor, no other ones. Okay? So the factor theorem would state that if you plugged in the b value, which of course the format is x minus b. So this x plus 1 is actually x minus a negative 1. So that's you put the opposite sign there. So if I want to check this factor, if I don't know if that's a factor, I'm going to do this over here. I'm going to put in negative 1 here. And that means wherever I see an x, I'm going to put negative 1. And I'm going to test this to see if this result is 0. If this is 0, then I have indeed determined that the x plus 1 is a factor. So let's just see. Negative 1 cubed is negative 1, so that's going to be negative 2. That's going to be negative 1 squared is positive 1, so minus 5. This is going to be positive 4 when you multiply those out, plus 3. So negative 2 minus 5 is negative 7 plus 7. Wow. That's 0. Awesome. Did you guys get that as well? Did I do that correctly? Okay. So that means that x plus 1 is a factor. It is a factor. Now we could check the others as well. There might be other factors as well. But usually when you start to factor something, you try and determine one binomial factor, a two-term factor, and then you can do synthetic division from there. But we could keep going too to see if any of these work. But let me just go over synthetic division. Now, I've got lots of videos for synthetic division, so if you need a full lesson on synthetic division, please feel free to watch that tonight. You will need this for calculus, especially in chapter 5. We're going to be doing lots of curve sketching. You have to do synthetic division. You have to factor polynomials and also do the unit analysis and stuff like that. So this will be coming back. Yep. Question?
3 or 7.
Okay. So yeah. So this question right. Oh, actually, 2x cubed minus 5x squared minus 4x plus 3. It's the same. Yeah. I'm sorry, I didn't hear what you said. That's the same one. Yeah. So the cube, this looks like a 7?
Yeah.
Okay. No, that's not a 7. That is a 3. So I can rewrite that for you. 3. Yeah.
In the manual it says long division, but
In the what, sir?
in the manual.
In the manual?
The
Textbook. Well, there is long division. There's polynomial long division, but there's also synthetic division, which is the shortcut for long division, if you remember back to pre-cal 30. So you don't have to do long division per se. Synthetic division is sort of the shortcut for that. So this really is long division of polynomials, but synthetic division is the shortcut. So I'll just kind of review the shortcut, I think. Yeah, I'll just review the shortcut. Yeah.
Yeah, is there ever a case where you have to use long division as opposed
Well, this is long division. It's just, it's just a shorthand. It's a shorthand version of it. So
there are like no drawbacks?
yeah, no drawbacks this one. No, I guess not. Okay, are you ready? So again, we're going to divide this polynomial by this binomial. First thing we need to understand is that this x plus 1 is in the form of x minus a. So I'm going to put minus 1 here. Okay? Put minus 1. The reason why I always put a there is because then you can always add with your synthetic division. You never have to subtract. Subtracting integers is where students get in trouble and make a mistake. Adding integers is much easier. So use the a value here in your synthetic division. There is a way you can do it by just using plus 1 here, but we're not going to do that. Okay? So the other thing is, two things. You want to put numbers on the top row of this, over top of this elongated L here. The numbers are the coefficients for the polynomial terms, but they are the coefficients in order, including all of the coefficients, starting with the highest exponent value. So I'm going to put a 2 here, because that's the coefficient on the term with the highest exponent. Then I have to locate the squared term and write down this number. So I'm going to leave a little space. I'm going to put minus 5 here. Again, this is shorthand for long division of polynomials. I'm going to go and I'm going to find now the x to the 1, which is right here, and I'm going to write down negative 4. And then x to the 0, which is what this constant really is, I'm going to write down the constant.
What do you do if you don't have a
Right on. If you do not have, if you're missing a term, then you have to place a 0 in there.
just the 0?
You have to place a 0 there. So if there was no x term, let's say, it was x cubed, x squared, and then a constant, you'd have to put a 0 in here for the x term. Yeah. All right. That's the setup. Any questions? Remember that? Okay. All right, so first thing we do for synthetic division is we drop this first number all the way down to the bottom. Now down here is where you're going to find the coefficients for the quotient when you divide. So you always drop the first one. Good. Now what do? Who remembers?
You
Times the 2 by negative.
Multiply -1 times 2, that's -2, and you put the result right there. Okay? Now what do we do next?
add them.
We add this column right here to get our answer of -7 right there. Okay, very good. And now we start the process over again. So now we just rinse and repeat here. So -1 times -7 is +7. Good. Add those. +3. Put that down there. Now rinse and repeat again. -1 times 3 is -3. Add 0. Now if you remember, I always, under the constant of the last term there, I always put a box down here. And that reminds me that this is the remainder. Okay? That's the remainder. And if x plus 1 is a factor, this should always be 0. So this is your p of -1 here, right? That should always be your remainder. All right, so what does that mean? That means that the factors that we have so far are x plus 1, which is already given, represented by this. And this represents the other factor. The other factor, this is the result of division. Now remember, this was cubed, so these coefficients start at x squared. Okay, you minus 1, so that's now 2x squared. This is -7 x to the 1, or just x. And this is plus 3. So that's how you use synthetic division to divide polynomials, and you will get down to a smaller polynomial, which you will still have to further divide by whatever means necessary. If this is a polynomial that's still more than 3 terms, you might need to do synthetic division again. But when it's 3 terms, a trinomial, there's a good chance you'll be able to do this by intuition or the decomposition method. Which again, if you want to learn about decomposition method, you'll have to maybe go back and watch that video. We'll try and do this by intuition. So let's see. I'm going to try and divide this, factor this into 2 binomials. The first binomial would have a term of whatever, factors of this. So I'm going to guess 2x and x. You have to have an x in each term, and 2 is prime, so 2x and x, that's where you go. Now 3 is prime as well, which means that there's only 2 factors, 3 and 1 in itself. So we're going to have a 1 in either this spot or this spot, and a 3 in either this spot or this spot. And are they going to be positive or negative? How do we know that?
Negative.
Yeah, they're going to be negative. Why do we know that?
The B term.
Because the b term is negative, therefore we're going to be subtracting terms to get a negative term. Awesome. So really quickly, you can do some mental math here. If I do 2 times 1, that's 2, and 3. So 2 and 3 is 5. Sadly, that does not give me 7. So what if I did a 3 over here and a 1 here? Does that work?
Yes.
A quick FOIL, 2x squared minus 6x minus 1x. Awesome. That gives me my -7. So that's how you factor that, just kind of by intuition or just mentally there. Okay? All right. Now your brain's mush here in the last period of the day? No, you're okay? All right, that was great. Awesome. Okay, yeah, so there's our answer. Okay, that's all I'm going to do to refresh your memory on synthetic division. Like I say, that won't come up first chapter or anything, or first or second even. It's going to come up later in the course, but something that you'll need to remember to do. And we will take some time before each chapter to review a couple of these if necessary. I'll review these before each chapter. So we will see this again if you need it. But
We're going to need it for the review though, right?
all right, the next thing we want to review is simplifying rational expressions. So a rational expression, think of the word ratio in there, and that's a ratio of some polynomial over another polynomial. And when we simplify those, what we're going to try and do is we're going to try and take out any common factors that we have from the top and bottom. So here are the steps to simplifying rational expressions. You want to write these down? I would encourage you to do that. If not, that's fine. You should know this already, but it's up to you. So step number 1. Remove any greatest common factors if possible. And when I say remove, I just mean factor out. I don't mean like take away. So for example, I will do step 1 here, and we have to kind of focus on the top and the bottom separately when we do this step, okay? So the top one, I can take out, looks like a what? I can take out a 2. Yeah, there's a common factor, for sure. So when you take it out, you need to put it off to the side. Don't just get rid of it. Put it off to the side, and then write what remains when if you were to divide that out of each term. Okay. So we do that for the top, and then we do that for the bottom as well. I see that I have a common factor of 2 as well on the bottom. Okay, easy stuff. Now, if we have the same factor on top and bottom, that's part of simplification. So you can remove those, really. So those divide out to give you 1 over 1. So we're not like eliminating them, getting rid of them. What we're doing is we're factoring them out to get to simplify to 1 over 1. So it's the same as being gone. Okay, you guys okay with that? I know this might seem like I'm being way too simple. You guys probably remember all this, but I'm just trying to be very clear and not to rush you too much here. I'll rush you later in the course, don't worry. No, I'm just joking. You like this pace? Okay, yeah, you like me going slow with stuff you've already learned. Awesome, okay, good to know. Good to know. That will end probably today. Okay. Okay. All right, step number 2, fully factor the numerator and the denominator. So again, we're focusing on each separately. Can I factor this top one? Well, probably can factor that into 2 binomials. The bottom one is probably not going to be able to be factored any further. So I'm going to put a 2x here and an x there. Now, 15 is not prime. Well, it's not prime, but it doesn't have very many factors. 3, 5, 1, 15, right? So what about 3 and 5? Usually when you're doing this, you start with the factors that are close to one another. Usually you start with those because most of the time those are the numbers you're going to want to work with. So if I just put a 5 here and a 3 here, quick mental math, is that going to get us anywhere near 7? So 2 and 5, 2 times 5 is 10, and 3, oh, that can get me 7. Well, let's figure this out. I need a negative 7, so why don't I make a negative 10 and a plus 3. You guys with me? So negative 10 plus 3 gives us that negative 7 we're looking for. So that's how I factor that. Now the nice part about this, okay, we've done that, we did this. The nice part about this is you can see that we're going to be able to simplify an entire binomial factor from the top and the bottom. That's awesome. But what we want to do first, before we divide those out, is this part right here. You can do this at the end, but you might miss something if you eliminate something and then don't go back and figure that out. So I would suggest noting restrictions at this stage, step 3. Restrictions would be any values for x that are not allowed or that make this mathematically impossible, which of course, one of those things is any x value or values that would make a negative under a square root. That's a common one. Or any x value or values that would cause the denominator in the expression to be equal to 0. Right, that's bad. So we can see that x minus 5, if x was positive 5, we'd have a problem. So you have to make note, x cannot equal 5. And we'll just kind of keep that in mind. So when we've simplified, we have to state that in our answer. Any other restrictions? Nope. We can have anything we want up top, right? Plus, minus, decimal, fraction, 0, anything. It's just the bottom we have those restrictions. Finally, divide out common factors. And here we see pretty plain that we have an x minus 5 as a complete factor. This is multiplied by 2x plus 3. And this is a complete factor on the bottom itself. So my simplified answer, or simplified expression, is just 2x plus 3 with this little caveat here that x cannot equal 5. And that would be your simplification. All right, we will, we'll talk later about what this means, right? Like if you were to graph this, what this means, do you guys remember? Actually, why don't I ask you, do you remember what this means? Like there's this, if you were to graph this, y equals that. If you were to graph that, what relation does it have to the simplified version in this? What, do you guys remember?
Pencil line with his cap ass.
Okay.
Or whatever it's
Okay, yeah. So the gap part I like. The line with a gap asymptote is a bit of a funny statement there. There's a little bit that doesn't work. But the gap part is perfect. Yeah.
It's like a gap.
Yeah. I guess you could call it a gap asymptote. It's not really an asymptote, but
Yeah.
but it does turn out to be a line. I like that. And at x equals 5, there is a gap or a small hole. So yeah, you're absolutely right. This function, if this were a function, it would actually look just like a line. This line 2x plus 3, but would have a hole there at x plus 5. So you pretty much got it right. Yeah. Yeah. Asymptotes are a bit different. They kind of like approach infinity, and it's it's a value that's not defined. This would be a gap. It's a gap discontinuity is what it's called. Discontinuity is the word you'd use there. But awesome. Okay, moving on. Rationalizing. Okay. Now, to rationalize a numerator or rationalize a denominator, you've done both. And if you remember back to Pre-Cal 30, when we did proving identities, remember that? When we did that and we had to rationalize out of the numerator denominator with sine, cos, and tan, all that. Anyways, yeah, you've probably repressed those awful feelings. I apologize for bringing those back up. But in order to rationalize means make rational, it means get rid of a radical, like this root sign here, because this term right here is irrational. So if you're asked to rationalize the numerator, and you may have to do that again to simplify something. So what you do is, and I don't have this typed out, the steps are what you do, but I'll write it down over here. You multiply by the, and it's called the conjugate. It's the conjugate, but it's the radical conjugate. It's the irrational conjugate, radical conjugate. Let's just say conjugate, okay? Conjugate. So you multiply by the conjugate, and it's obviously the conjugate of the expression you wish to rationalize, okay? Yeah. So if you remember what a conjugate is, it has the same terms but opposite sign. If it's a binomial conjugate, same terms, opposite sign. So that's what we're going to do. Multiply the top and the bottom. I should put that in there too. Because you don't want to change this expression. You just want to change how it looks. So same terms but opposite sign here. Now, how is this going to change anything? Well, it's just like multiplying by 1 over 1, right? So we're not actually changing the value of this. But what this is going to do, if you notice this right here, when you multiply these out, this is the format of a factored difference of squares, right? That's a factored difference of squares. So when you multiply this out, do the FOIL method, root x plus 4 times root x plus 4 is simply x plus 4. This is going to be, you're not going to write this, but this is going to be 2 root x plus 4, and then you're going to have minus 2 root x plus 4. So those are going to cancel out. And then finally you're going to have negative 2 times 2 is plus 4. So do you see how by multiplying this up top, I get rid of the radical? It's gone. And then down here, well, a little hint, you don't have to multiply all factors together all the time in calculus, because you may have a simplification, a dividing out of factors that you can do. So if you go ahead and multiply all the factors, well, now you've lost track of what the factors are, and you may miss a simplification. So obviously multiplying the top ones are important to rationalize, but little hint, a lot of times in calculus, you can just do this and not multiply that out, and what you'll end up seeing is you might see a factor you can divide out. Now, in this case, whoa, I put plus, and I should have put minus. That's wrong. So thank you. No one caught that. In this case, we do have a common factor on the top and the bottom, right? Yeah, because I think I said negative 4, but wrote positive 4. Okay, so you see how we have x and x as common factors? So this actually simplifies to 1 over root x plus 4 plus 2. And you may think, well, how is that any better than what we started with? There will be reasons you'll find this term in calculus that you will want to express this without a radical in the numerator and instead a radical in the denominator, that may help you. It might simplify things. And vice versa. You might want to rationalize the denominator. Okay? So anyway, so that's how you rationalize the numerator. Notice that there's no radical anymore in the numerator there. Any questions about that? Yeah. You may just need to do that at some point. Okay. Multiply. I'm going to put top and bottom by the conjugate. Okay, just so we're clear there. Okay, go ahead. Why don't you take a moment, take a few minutes here, and go ahead and rationalize the numerators on each of these, and I'll show you the solutions in a few minutes. First. Okay, so reminder, what you can do is 1 over root x is the same as 1 over x to the 1/2 or x to the negative 1/2. So if you like that better, this is what I started to do over here for b. You don't have to do it this way, but when you multiply these out, remember you add exponents when you have bases that are the same, you add exponents. So a FOIL method here, this would be x to the negative 1, right? And then it's going to be a difference of squares, we know that, so it's going to be minus 1. Now this down here gets a little bit funny, but what is this? What's 1 plus negative 1/2? This is going to be what? Oh, well, hang on. This is the negative 1 minus 1. X to the positive 1. Yeah. Okay, so it's going to be x to the 1/2. X to the 1/2, okay. And then if you're multiplying these out, it's going to be plus x minus x to the negative 1/2. Because you're multiplying these, right? And then minus 1. Okay. So this is 1 over x minus 1. This is going to be, now, is it a good idea for us to multiply that out? We might be missing some factors here if we multiply this out. Remember what I said before? So well, let's just follow it through. Are there any like terms we can gather? To gather like terms, they have to have the same base and the same exponent, right? So these don't have the same bases. Well, they don't have the same exponents. So that's going to be, this one's going to be a little bit tough for us to do, isn't it? So let's go back and not multiply these out. Let's go back and not multiply those out, and let's leave them as x minus 1 times. This is going to be root x plus 1. You might want to go back to the roots there. I don't know. Yeah, 1 over root x. Sorry, 1 over root x plus 1. This is x to the minus 1/2, so it's 1 over root x plus 1. I'm kind of doing two different methods at once here, so, because you guys asked. Okay. So this minus 1, that's actually x over x, right? So this is 1 minus x over x minus 1 over root x plus 1. So I'm going a little fast here. But when you have the fraction like this now, right, divided by something else like this x in the denominator here of this fraction can just come down to the full denominator there. Right? So it can be written like this: 1 minus x over this x is now a factor in the bottom, as well as these other things. And we're getting close to being able to divide out something. Do you see how 1 minus x and x minus 1 is almost the same? Do you remember how you do that? Yes, you take out a negative 1, and this then, if you have a negative 1 as a factor, then this becomes minus 1 plus x, which is the same. Same as x minus 1, so those are gone. Again, the question was rationalize the numerator. That's all we needed to do. So we are good there now. Now with this, you can stop for sure. Negative 1 over x times 1 over root x plus 1. And you've rationalized the numerator. You're done. Could we have stopped sooner? Well, you don't want to leave a fraction inside of a fraction. So, well, we have a fraction inside a fraction down there, I guess. So,
Could we stop at like
Here's my other solution here. 1 minus x. Yeah, so you could have stopped a bit sooner. You could have stopped a bit sooner there. That would have been fine, I guess. As long as the numerator is rationalized, then you could stop.
Okay.
Yes?
The back has it as -1 over x plus root x.
Yeah, so what you guys will find, good question. What you'll find is the answers in the back, because there's many different layers or stages of simplification. You might find, and this will happen all throughout the course, that you'll find that your answer might not match the answer in the back of the book when you check, but it's probably just a simplification issue. You might still be right. So we could go further and I could multiply this in. I could actually go further and have another sort of way to show this. But this is where we could stop. You could stop up here too, and so on. So, all right, that got a little tricky at the end here. Okay, here's your review and preview, page 3. There's your full assignment. Please work on those before tomorrow, and then we'll move to 1.1 tomorrow.
What's 1.1?
What's 1.1? The first section in the first chapter.
Yeah.
It's called the tangent problem. Bum, ba, da, ba, the tangent problem. All right, here's the website. Basics, there we go. And 1.1 coming. Oh, look at this. I'm gonna put this lesson I'm recording right now just in there for you. So 1.1 tangent problem. Dun, da, da, da. Big time suspense right there.